Okay, so today we're going to review normal distributions. So first of all, what does it mean for a data set to be normally distributed? Basically what it means is that if you take a look at its histogram, if you take a look at sometimes it's called a frequency graph, what it means is that it follows a bell curve. Okay. There's a more technical definition, but this is a good enough definition for us. There's some central value here, which is called the mean of the distribution. It's the average of all the elements in the distribution. And the basic idea is that this graph is sort of telling you how common different elements of different values are within the data set. So, you've got some data set with a whole bunch of numbers, 2, 7, 11, maybe 7 again, 12.5. You just got some gigantic data set with all kinds of numbers. And, if you have a distribution that looks like this, centered around 6, what that's really telling you is that elements close to 6, like 6 itself, or 7, or 5.5, elements close to 6 are very common. That's why the graph is very high here. And as you get away from 6 and you begin to look at elements further away from 6, those elements are a lot less common. Okay, so there's a more technical definition, but roughly speaking, being normally distributed means that there's sort of some, mean, right, an average value, and the data set is symmetrically clustered around that value, tapering off, and the further away you get from this element, the less common those guys are. So most of the elements in the data set in this case would be close to 6. Elements that are far away from 6, like say 50, may appear in the data set, but they're very rare. Okay, so that's kind of what it means to be normally distributed. Now, the thing that we have to talk about is that there are, in fact, many different normal distributions. Okay, there are many different normal distributions, and in fact, a normal distribution is really determined by two parameters. These are like two knobs that you can adjust in order to change the shape of the distribution. So the two things which determine the shape and location of a normal distribution, the two things that determine the normal distribution, are the mean, which we represent by the Greek letter mu, and the standard deviation of the distribution, which we represent by the Greek letter lowercase sigma. Now, what exactly do these two things do to the distribution? Well, adjusting the value of mu, that is the mean of the data set, simply changes where the normal distribution is centered. In this picture I drew here, the distribution is centered at 6. Whatever mu is, whatever the mean is, that's where the distribution is going to be centered. So if you have mu is equal to 2, then you're going to have your distribution centered at 2, and if you have your mu equal to -3, then it's going to be centered at -3. So changing the value of the mean mu basically just shifts the graph left and right. Well, what does the standard deviation do? If you remember from last year and from the homework, standard deviation is a measure of the spread in the data. It's like how spread out the data is. So adjusting sigma, the standard deviation, controls how flat or spiky the distribution is. So, for example, imagine that I have a very small value of sigma. If you have a very small value of sigma, a very small standard deviation, that means that your distribution has very little spread. Okay? So whatever your mean is, whatever mu is, if you have a small sigma value, that means you have very little spread in the data. That means that your data is very highly concentrated around the mean. Okay? That means your distribution will look something like this maybe, big tall spike right at mu. And what this is telling you is that the vast majority of the data is very close to the mean mu, and very little of it is far away from the mean mu. So that means that the data is very highly concentrated, very little spread. On the other hand, if you have a big sigma, if you have a large value, for the standard deviation, that means that there's a lot of spread in your data. That would mean that your distribution would be perhaps a lot more flat. What that's telling you is there's quite a lot of data that is sort of further away from you. It is not as tightly concentrated around the mean as it is in this first distribution. Okay, so we have many different normal distributions, okay? One for every choice of mu and sigma. So actually there's an infinite number of normal distributions. Pick a value for mu, pick a value for sigma, and that gives you, a unique normal distribution. Now, there's one special normal distribution which we like to single out as kind of a reference, and that's the so-called standard normal distribution. So the standard normal distribution is just the normal distribution with the mean of 0 and with standard deviation of 1. Okay, so there are many normal distributions, one for every choice of mu and sigma, but there's one particular normal distribution that we like to single out and give a special name, and that's the standard normal distribution, and that's simply the one corresponding to mu equal to 0 and sigma equal to 1. Now, you have in the homework, you have this table that I gave you, this z-score table. This is something that you've used, in previous years, and we just need to review sort of how it's used. Every single one of these values here refers specifically to the standard normal distribution, okay? And we'll see what those values mean and how to use them in just a second. So here's the idea. Let's take an example. Suppose that you have some data set. I don't care what it is. Maybe it's just some list of numbers. Suppose you have a data set, and let's say that it follows the standard normal distribution. So not just any normal distribution, but let's say that your data set specifically follows this one here, right? Okay, so that means that the data set is centered at 0 because the mean is 0 and the standard deviation is equal to 1. Okay? Now suppose I asked you the following question. What percentage of the data is less than, let's say, negative 0.56. Negative 0.56. Okay? It turns out that the answer to that question is the following. Go to negative 0.56, which I don't know exactly where that would be. It would be somewhere to the left of 0. Let's say it's right here. The percentage of the data in our data set, which is less than negative 0.56, is actually going to be the area to the left of negative 0.56 under the curve. Okay? So it's the area of this region here. I want to emphasize this curve actually goes on forever and sort of asymptotically approaches the horizontal axis. So this region is sort of like infinitely long, even though it's actually finite in area. Kind of a strange concept. Infinitely long, but finite in area. It's not common to see something like that, but that is the case here. So anyway, the percentage of the data less than negative 0.6 is just the area to the left of negative 0.6 underneath the standard normal curve. Now, what is that exactly? Well, areas to the left of values are exactly what these things are right here. Okay, so if you want to find the area of this region, and we do, you just have to look up negative 0.56 in the z-table. So that's a z-value, right? That's what appears in this column here. So I need the negative side of the table. So I'm going to go to the negative. So I want negative 0.5, and it's 0.56. So to get the next decimal place, I look along here. So let's see, negative 0.56. So negative 0.56 is going to be the intersection of this row here. This column here looks like 0.2877 right down there, right? Negative, or 0.2877. So the area of this region is 0.2877, meaning the percentage of data which is less than negative 0.56 is like about 28.77%. Okay, about 28.77%. So questions about the percentage of data correspond to areas under the curve. And that's the basic idea. So like if you wanted to know, you have a data set once again following the standard normal distribution, and you once again want to know, what percentage of the data, say sits between, let's say sits to the right of 1.13 or something, right? If you want to know what percentage of the data is bigger than 1.13, that would actually just be the area to the right under the curve of 1.13. So yeah, if you want to know what percentage of the data is bigger than 1.13, that would actually just be the area under this curve to the right of this value. Now, how do you find that? What I want to emphasize is that all of the values that appear here, these are all area values. These are all the areas of different regions underneath the curve. But they're all areas of particular. So one important fact is that the total area underneath the normal curve is going to be 1. And the reason why is basically areas under the curve correspond to percentages of the data. Obviously, 100% of the data is encompassed by the curve, so 100% is 1. So the total area under the curve is actually 1. So if you want to know the area of this region right here, the area to the right of 1.13, and what you can do is take 1 minus the table value for 1.13. Let's look up what that table value is. 1.1 is here, and then 1.13 gives me 0.8708. So 1 minus 0.8708, that's going to give me this region here. And the reason why is, obviously, this shaded region here can be viewed as the entire region under the curve minus this white space. And this white space is exactly a left region, right? It's a region to the left of 1.13 underneath the curve, which is exactly what that 0.8708 figure is giving us. And finally, if you have like if you have a region like this, which is sort of bound on both sides, maybe it looks like this, then what you need to do is find the table value for this guy and subtract it from the table value for that guy. So you look up the area associated with this, you look up the area associated with this, and you subtract them. And the reason that works is that the area associated with this value, the 1.13, underneath the curve, is going to be everything to the left of 1.13. That's all of this area and all of the white space all the way out to negative infinity. Well, we don't want that, right? We don't want everything to the left of 1.13. We just want this shaded region here. So what you do is you take the table value associated with this guy, which is everything to the left of 1.13, and you subtract the table value associated with negative 0.56. That's just the area of this white space. So you take everything here, and then you subtract off the white space here, and you're left with the shaded region here. So hopefully that's kind of familiar to you. It's something you did last year. What we need to talk about, though, is the fact that, all of these table values correspond to areas underneath not just any normal distribution, but specifically the standard normal distribution. That's the normal curve with mu equal to 0 and sigma equal to 1. In real life, most data sets which are normal don't follow the standard normal distribution. They follow some other normal distribution. Like if you're considering the heights of everybody in the United States, maybe that's normally distributed, but the mean height isn't 0, right? I mean, the mean height is maybe like 5.5 feet or something, or 5 feet. Certainly not 0. So it's not a standard normal curve. So the question then is, how do we work with non-standard normal distributions? And the answer is basically we have to use this z-score conversion formula. So here's the z-score conversion formula. Z is equal to x minus mu over sigma. And I'll explain exactly what this is. So here's the key fact. The area to the left of x under a normal curve with mean mu and standard deviation sigma is equal to the area to the left of z under the standard normal curve. Okay, and that's kind of abstract, so I'll draw you a picture. The basic idea is the following. Suppose you have some non-standard normal distribution with a mean mu. Okay, so this is non-standard. You have a mean mu, and the standard deviation is sigma, whatever sigma might be. And suppose you want to know what's the area to the left of this value x right here. Okay, suppose you want to know the area of this region right here. Well, the thing is, this table can't help you because these are all areas under not this normal curve, but the standard normal curve, which we don't have, right? Our mean is not 0, it's something else. And our sigma is not necessarily 1, it's something else. This key fact tells you that the area to the left of x under this non-standard normal is actually going to be the same as the area to the left of z, which is defined by this formula here, to the left of z under the standard normal. So here's the standard normal. The way I drew it, they look pretty similar, but in general they might not look the same. And the idea is that the area to the left of z, given by this formula under the standard normal curve, is actually the same as this area here. Exactly why that's true, I mean, it's not exactly obvious. It requires some work to prove. We won't be doing it, but you can just take it as an accepted fact. So let's just do 2 examples, sort of making use of this. So let's suppose that we have a data set that is normally distributed, okay, but not the standard normal distribution, but some other distribution. Let's say mu is equal to 100 and sigma is equal to 10, okay? Here's a question. What percentage of the data is less than 95? Okay, that's the question. Now, the answer to that question is the following. You take a look at your distribution, which is centered at 100 and which has a sigma value of 10. So you look at whatever that normal distribution is. The percentage of the data less than 95 is just going to be the area under this curve to the left of 95. Now, how do you compute that? Well, what you do is you say, if I use this z-score conversion formula, x minus mu over sigma, x is the value you're trying to convert. That'd be 95 here. So 95 minus mu, which is 100, over sigma, which is 10. If you simplify all that, you get negative 0.5. So there's this magic fact that we just talked about here, which says that the area to the left of 95 under this curve is going to be the same as the area to the left of negative 0.5 under the standard normal curve. Okay, those 2 areas are going to be the same. And this area is something we can actually look up, right? That's something we can look up for our table. So we just go to our table. We need to look up the z-value of negative 0.5. I guess that would be like negative 0.50, which is the first column here, right? So that would be 0.3085. So this region here has an area of 0.3085, which means that this original region here also has an area of 0.3085. So what percentage of the data in our distribution is less than 95? The answer is 30.85%. Okay, that's how that works. Okay, so let's do one more question. So suppose that the SAT test, right? Let's suppose that SAT scores are normally distributed with a mean of 1,000 and a sigma value of 100. I'm just making these numbers up, but let's just pretend that that's true. You have normal distribution. It's not the standard normal because mu is not 0 but 1,000, and you have sigma equals 100. And here's the question. What's the 95th percentile? What does that mean? The 95th percentile is the score such that it's better than 95% of the other scores. So getting 95th percentile means you scored better than 95% of the people. So here's the idea. Here's our distribution. It's centered at 1,000, right? Maybe it looks like this. I don't know. And, obviously 1,000 being the mean is better than exactly 50% of this other scores, right? So this would be the 50th percentile. And we want to know, where's the value x, which is better than 95% of the other scores. So this is better than 50%, maybe this is better than 60%, 70%. Eventually you're going to get to some value which is higher than 95% of the other scores. And we want to know what is that x value. That's the question. Now, the way to understand it is that if this thing is bigger than 95% of the data, that means that the area of the shaded region here to the left of that x value is actually 0.95. Okay, that's what that means. Now, in order to find this x value, what I do is I actually consider the standard normal curve. Okay? Now, under this standard normal curve with mean 0 and sigma equal to 1, I can find the value z, which is bigger than 95% of elements in the standard normal distribution. That I can find. Okay? Now, 0.95 is an area value, and what I want to do is find the z value which corresponds to it. A little bit backwards from what we've been doing previously, where we knew the z value and we were trying to find the area. What I do is I go hunting for the closest thing to 0.95 that I can find. All right? I see kind of two values that could be used. This one here and this one here, they're equidistant from 0.95. When there's a tie, you can just pick one. I guess I'll go with this one, the 0.9495. Now, what z value does that correspond to? Looks like 1.64. So 1.64 is the z value in the standard normal, which is bigger than 95% of the data. Now, I want to know what's the corresponding x value. Well, I can use the z-score conversion formula just like I did before. The only difference from the previous problem is that now I know z and x is the unknown. So I have 1.64 is equal to x minus mu, which is 1,000, over sigma, which is 100. And I can solve this thing for x. So multiply by 100, I get 164 is equal to x minus 1,000. Add 1,000, I get 1,164 is equal to x. So that is the value which is bigger than 95% of the data in